Good day, students. So today we are going to see about the semiconductors. So in the previous class we have studied about the basics of semiconductors, the types of semiconductor based on its purity and also the based on the materials used, right? So there are about two different types of semiconductors, intrinsic and extrinsic semiconductor. So intrinsic is the pure form of semiconductor, and extrinsic we get the extrinsic semiconductor by addition of some foreign atoms. Okay, so the addition of that foreign atoms, which is said to be doping, and we will get two different types of extrinsic semiconductor, and they are called as, based on the dopant, it is called as N-type semiconductor and P-type semiconductor. So these things already we have discussed in the previous class. Okay, so today let us see about the carrier concentration in an intrinsic semiconductor. Carrier concentration in an intrinsic semiconductor. In an intrinsic semiconductor. So for that we will see the energy level diagram first for an intrinsic semiconductor. So for an intrinsic semiconductor, we have a valence band energy, and below that lower energy levels. Okay, so it will start from minus infinity, and this is the valence band energy EV, and with an energy gap. So the higher energy level, the first position of higher energy level, that is the conduction band energy, and that too increases. So the maximum energy level, so that can reach the infinity, plus infinity, minus infinity to plus. So this is EV, this is EC, and the Fermi energy level, that is exactly in between. Okay, right now the electrons will present in the valence band. Electrons present in the valence band, and by the applying some energy, the electrons will move towards the conduction band energy. That means it becomes free. So at the same time, here it forms two holes. Okay, so the number of electrons, number of electrons in conduction band energy or conduction band is equal to number of holes in valence band. Okay, if two electrons are there, two holes will be present here, and if it is more than that, if it is 4, then 4 holes here, so it will be, both are equal. Okay, right. So this is the energy band diagram for an intrinsic semiconductor. So this is very important to understand the concept. Now we know that to find the number of electrons. Okay, so first topic in order to find the carrier concentration in an intrinsic semiconductor. So for intrinsic semiconductor, you know that both the electrons and holes, so both these electrons and holes are responsible for the conduction. So we should okay, let me write in the next page. So we should calculate the density of electrons in conduction band. Electrons in conduction band. So first let us find the density of electrons in the conduction band. So for that, in order to find the electrons, n is equal to, so from the energy level diagram, okay, so in the energy level diagram, so here you can see this is minus infinity EV, and the electrons are present above this conduction band energy, so EC to infinity. Okay, so here you can write EC to infinity, and E set of E, there is a number of energy state, into F of E, the probability of finding an electron, that is a Fermi distribution function, into dE. So the number of electrons is given by the product of the number of energy state multiplied by the probability function within the limit EC to infinity. Okay, so the number of electrons will present in between EC and infinity. So let us put this as equation number 1. Okay, let me tell you. So let me write this. Z of E into dE. This is the density of energy states. Density of energy states. And F of E, so as you know, it is a probability density function, distribution function. There is probability of finding electrons. Probability of electrons in conduction band. So let me write it as CB. And EC, you know, the starting energy of conduction band, then infinity is the maximum energy. EC starting energy of CB, and infinity the maximum energy of CB. Okay, so this is the equation. Now using the density of states we have obtained from the metal, cubical metal piece. Okay, so from that we are going to derive these things. So now let us see Z of E into dE. Okay, so this is what we are going to write is from the previous unit, that is density of states in a metals, energy states in a metal. So let me write that 4 pi by h cube. So we have written as 2m star. So here it is 2m e star. This is the effective mass of electron. So that is power 3 by 2 then e power 1 by 2 into dE. So now based on this density of electrons in the conduction band, we have some modifications here. So let us do that. So here this, if you consider an energy level, that is a higher energy level. If E is the higher energy level, okay, so here it is goes up to infinity. So we can consider that as E. So that is the maximum energy. Okay, so maximum energy minus minimum energy. So we can write this E as, so the minimum energy in the conduction band. So here minimum energy in the conduction band is EC, and this maximum energy, so we are taking as E. So within this energy level the electrons will present. So we can write as this equation can be modified. So put this as equation number 2. Okay, so here equation 2 becomes Z of E into dE is equal to 4 pi by h cube 2 me star power 3 by 2. So instead of E, you have to put the maximum energy minus EC, E minus EC power 1 by 2 into dE. Okay, so this is put this as equation number 3. So already we know the value for f of E, that is the Fermi energy distribution function. So f of E is equal to 1 by 1 plus e power capital E minus EF by kT. That's the Boltzmann constant, and T is the absolute temperature. So we got this value Z of E into dE and f of E. So in the first equation, so here you see n is equal to EC to infinity Z of E into dE f of E. So we got these two equations. Now substitute this 3 and 4. Substitute equation 3 and 4 in equation 1. So while substituting that, you will get n is equal to, so take the common terms outside, only the changing terms. So that will be taken inside the integration. 2 me star power 3 by 2 integral of so you can write EC to infinity and what are things, E minus EC, E minus EC power 1 by 2. So f of E is there, that is 1 by 1 plus e power E minus EF by kT into dE. So we got the equation after the substitution. So put this as equation number 5. So here we are going to change this derivatives. These derivatives are now in terms of E. Okay, so we are going to change in terms of X. So for that, let us have a consideration. and we are going to change everything in terms of x. And one more thing is there. Okay, so before the consideration, we have one more thing to do. So in this equation, that is equation number 5, the kt value is very small. Kt value is very small. That is the value in Fermi distribution function. So what happen means this E minus EF value is very high. Since E is taken as the infinity, it's a very high value. Now what is the condition means exponential of E minus EF by kt, that is very large when compared to 1. Okay, so that means the denominator value is very much higher. So you know the here you can see 1 by 1 plus e power e minus e by kt. So here okay, so in the denominator 1 plus this value. So this exponential value is very much greater than this 1. Okay, so here it is very large when compared to 1. What happen means that particular value is just written as 1 by e power e minus ef by kt. So 1 can be neglected. 1 can be neglected. So after neglecting this, you will get n is equal to 4 pi by h cube 2 me star power 3 by 2 integral of ec to infinity, and inside you have e minus ec power 1 by 2, and we are taking that to the numerator. So 1 by 1, 1 is already neglected, so 1 by e power e minus ef by kt. So that can be written as e power minus e minus ef by kt into dE. Okay, so this is taken like this. Now in this exponential form, we have to take this ef outside. So this is as a whole minus means it will becomes e power ef, this will become plus, so ef minus e by kt. The next step we can write 4 pi by h cube 2 me star power 3 by 2. Here you take this exponential of ef by kt, and inside the integral value you have ec to infinity e minus ec power 1 by 2 and the remaining term is e power minus e by kt into dE. This is equation number as per our, so this is equation number 6. So we come up with this equation. Okay, so this from this equation we are going to change the energy derivatives in terms of x derivative. So let us see how to change that. Okay, so to solve this, let E minus EC is equal to X. So here you have to put X. Okay. So now E is equal to EC plus X. And if you have change in DE, then it becomes DX. DE becomes DX. And okay, so now you apply the limit when E is equal to EC. When E is equal to the lower limit EC, so what will happen? E is equal to EC. So here you see X is equal to, in the first case, EC minus EC, that becomes 0. X is equal to 0. Then when E is equal to infinity, E is equal to infinity. So infinity minus EC, so that is a higher value, so that becomes again infinity. So what will you get? X is equal to infinity. So X is also equal to infinity. Okay, so now let us substitute everything here. N is equal to 4 pi, N is equal to 4 pi by h cube into 2m e star e power ef by kt. So up to this no problem. Now here you have to start the okay, so instead of EC you have to put 0 to infinity. E minus EC is already taken as x power 1 by 2. So exponential of minus E, so that can be written as minus EC plus x by kt. That means minus EC minus x by kt. So dE is equal to dx. Okay, so substitution is over. We have substituted everything. So if you don't put the bracket here, so it will becomes minus x minus EC minus x by kt. So we just omit this bracket, minus EC minus x by kt. Okay, so now you can take e power minus EC outside. So we'll get, already you have a EF here, so this becomes e power EF minus EC divided by kt. So the only term here it is exponential of minus x by kt into dx, right? So let us go to the next slide. Now n is equal to 4 pi by h cube 2 m e star power 3 by 2 and you can write e power ef. Already I told you to take that EC outside, so e power ef minus EC by kt, integral of 0 to infinity. Inside you have x power 1 by 2 and x power 1 by 2, e power minus EC is taken, so the remaining term is e power minus x by kt into dx. So here this particular term, this is integral value, it is a gamma function which takes the value, since this value takes is x power 1 by 2 e power minus x by kt into dx. So that will takes the value as kt power 3 by 2 into pi power 1 by 2 divided by 2. So this term is multiplied here. Okay, kt power 3 by 2 pi power 1 by 2 divided by 2. Okay, so you just consider instead of this term, instead of this particular term, we are going to write this value, So here this value has power 3 by 2, this power 1 by 2, and this 2 is here. So this 2 and this 4 will get cancelled. So you can write 2 pi. Okay, so 2 into now let us take all the 3 by 2 power 3 by 2 values inside the bracket. So here pi, so already 2 me star is here, so you can write it as 2 pi me star, and already we have, okay, so this pi, and here pi power 1 by 2, so that's why I have taken here. So 2 pi me star kt power 3 by 2, so that is taken here, kt divided by, so this h cube can be written as h square, so the whole power 3 by 2. So this h square power 3 by 2 means 2 will get cancelled, so there will be no change in the meaning, h cube, and e power ef minus ec by kt. Okay, so n is equal to, this is the value, density of electrons in conduction band, and we have to find the calculation of density of holes in the valence band. Okay, so that we will see in the another one video. Thank you.